Okay. Um, Today we're going to be looking at standing sound waves, and these would be things like you might have in tubes. Tomorrow, when we meet, I can show you a bunch of demonstrations for these things. And then I'm going to have you experiment with some making your own standing sound waves in tubes and looking for places where they resonate. And you'll be using some electronic devices we have that'll generate the sound that you kind of drive the tube with. And they'll be pretty quiet until you find a resonance, and then they can get surprisingly louder. And it's sort of interesting to see that effect. So we'll be experimenting with that. But anyway, I'm recording now, so we can go on from here. For a lot of what we'll do, we'll imagine that we have a pipe, and your book draws them horizontally. I tend to do them vertically so I can fit more of them right next to each other. This would be a pipe. Actually, all of the pipes they demonstrate are open at one end and closed at the other. Although the way they show them as open at one end ends up being a place where it's driven by something. And the equivalent that they might have for this thing that's open at one end and closed at the other would be they draw it like they sort of show a bunch of pressure weight in here. And then this thing might be like a mouthpiece where somebody blows wind or blows air into the thing. And so you might have something like this. And you can see this is closed at that end, but you treat this end as an open end, even though it's got this partial block here, but you treat this as an open end. And so I like to draw them just like that. It's a little easier, well, easier to draw for one thing, but that's something to keep track of. If you have a closed end of the pipe, this ends up being what's called a displacement node. And the reason for that is that the air molecules here can't go beyond this point. And so now that's a little hard to picture with this kind of an open or a closed end to the thing, to try and picture it as being an open end, but just sort of accept that. Anyway, closed end. And it has to be a displacement node. And then that just means it's a place where the air molecules there don't go back and forth in simple harmonic motion like they would somewhere else. However, this ends up being a pressure antinode. So pressure. So that's something that'll happen. And the reason it is that, well, the air molecules here can't go anywhere. The air molecules above it can get scrunched up against it and then come off of it. And so you can have, when they get scrunched up against it, the pressure goes high. When they come back off of it, the pressure drops back down again. And as you've got these waves that are going back and forth in this tube at the same time, and try to picture that for standing waves. I think they've got some good standing wave demonstrations on that one website, but try to picture that you've got waves going back and forth, but it ends up generating a standing wave where you end up with this displacement node down here. And the way we could draw that is do something like this, where the width between these two lines that I just drew signify the amplitude of the displacement wave that's standing there. So right here, the distance between the two lines I drew is 0. That would be a place where the air particles don't go back and forth. Now, they're not going back and forth in this direction. They're going back and forth in this direction. So down here, the air particles right up against the stopped end of the tube are not going to be vibrating back and forth. They're just kind of stuck there. But the air particles that are up here will have a maximum displacement back and forth here. Now, any place there is a displacement displacement antinode, and so I'll label that here. There'll be the opposite sort of node for the pressure. This will be a pressure node up there. And one way of realizing that is that this end is open to the outside atmosphere. It's going to be sitting at the same pressure as the outside air is all the time. So these things are kind of confusing to try and get. But this would be the fundamental mode of vibration for this particular pipe. That's the lowest frequency that you can have in there. Lowest frequency corresponds to the longest wavelength. For a lot of what we're going to be doing here, we're going to be using this V is equal to F lambda. This is the speed of sound in the air for the most part. And so if you have a long wavelength, and this will be a long wavelength because this L here for this particular thing is only 1/4 of a wavelength. To get a full wavelength, you have to, actually, here's what a full wavelength would look like. You'd go from one node to another node. That's only half a wavelength, and you have to go all the way to another one. So this is what the wavelength looks like. And in this fundamental mode of vibration, the lowest note, that's only 1/4 of a wavelength. And so that's what you'll happen to have there. Now, keeping this V equals F lambda in mind, the frequency of any wave is going to be V divided by the wavelength. Well, in this case, the wavelength is actually going to equal 4L. So we would have V over 4L for the fundamental frequency. Now, the speed of sound in air, we're going to just leave it at 344 meters per second. The last example problem I'm going to do, we're going to consider speed of sound in air and speed of sound in helium. It's the only problem I'm going to do, and I'm not going to have you do any where you would have to use this particular formula, but it's just kind of interesting to do it for one problem. But anyway, that's the fundamental note that you could have in here, is that V over 4L. Let's see. I need some more clean paper here, I think. But not 11 by 17. I guess I could do that. Oh, well. Let's do some more pictures of this, considering these ideas. And I'll just draw a few of these. Start off with pipes, which are closed at one end and open at the other. And so, and the book goes through this. In fact, these are the drawings from the book, the way that they make them. I just like them vertical. It's a little simpler. So, okay, and in every case, the length of these pipes is L. And I just drew the fundamental, the lowest frequency here. And if we keep in mind that the frequency is going to be the speed divided by the wavelength, or the speed would equal the frequency times the wavelength, then in this case, we had that the wavelength was 4 times the length of this thing. So this would be V over 4L. Okay, and then what's the next possibility? Well, we have to have a displacement node at this end, but the next possibility is where you would have a second displacement node in this thing up about here, about 2/3 of the way up that thing. And here's what the standing wave would kind of look like. And keep in mind, I'm drawing a displacement wave here that has a displacement node at the closed end and a displacement antinode at the open end. But this next frequency that can occur in this pipe has a second displacement node in here. So here, right at that spot, there'd be a displacement antinode. So that's a place where the air molecules there vibrate the maximum amount. Here, they don't vibrate back and forth at all because it's a node again, and then another antinode up here. Well, this is actually, it's half a wavelength from here to here, and this is another fourth of a wavelength. And so that's 3/4 of a wavelength in the length L. And again, the total pipe length is L. We're staying with the same pipe length. So we have that L is equal to 3/4 of a wavelength, or the wavelength is 4/3 of L. I think that's right. Let's see, 1/2 and another quarter. Yeah, that's correct there. So what do we get for the frequency of this one? Well, it's going to be V over lambda, but that's V over 4/3 L, or the frequency of this one is, take that fraction and multiply it, it'll be 3V over 4L. Well, the frequency of this one was V over 4L. The frequency of this one is 3 times as high. So it'll be 3 times the frequency. I can play you what that sounds like. If you go from one note to something 3 times as high in frequency, you'd get that kind of a jump in there. Okay, so that's 3 times the frequency in the jump. Okay, I was doing 2 different strings on a guitar. It's just what that happens to be. I'm going to cross this one out and go to the next one that could occur here. And in that case, let's see, instead of having a single extra node here, we're going to have yet another displacement node. And so we'll always have one down here. Let's see, we'll have something like this going on is what we'll have. We have a displacement antinode at that far end. And practice drawing these things just to try and picture what's going on. Okay, distance between nodes is always half a wavelength. I didn't space these very accurately, but this would be half a wavelength. This would be half a wavelength. Distance from a node to an antinode is always 1/4 of a wavelength. So in this case, the length L has 5/4 of a wavelength there. The frequency then is going to equal V over 5/4 L, or flip that up there, we'll end up with the frequency equaling, let's see, did I get that right? No, the wavelength is going to be 4/5 L, excuse me. So that should be 4/5 down here. Okay, I had it wrong. Anyway, scribble that out. It's V over 4/5 L. Didn't do my math right. Anyway, invert that and multiply, and you'll have this frequency end up being 5V over 4L. Okay, well, that's 5 times the frequency of that one. I don't know how I would demonstrate that for sure, but notice this is V over lambda, or V over 4L. This is 3 times V over 4L. This is 5 times V over 4L. As we go up, this would be what's called the first overtone. This would be the second overtone for that pipe. But as you go up, you keep adding additional half wavelengths into this thing. And the next one up would be 7V over 4L, and then 9V over 4L and stuff like that. And you can get these things to vibrate. I think I'll be able to, with one demonstration thing I have, I'll be able to produce this one, and the next one up, and maybe one beyond that. Turns out I can't make it with the thing I'm thinking of. I can't make this frequency happen, but I can make these other ones happen. So anyway, that's what we get for the closed-in pipe. And the frequencies that are produced in that kind of pipe, we'll just go F sub n. It's going to equal N times V over 4 times the length. And in this case, N is going to equal 1, 2, 3, and so forth. And you can get all those different frequencies going on in there. So kind of neat that you can have stuff like that happen. And you can produce some of these things yourself if you have a hollow tube that's closed at one end. You can get various things. Anyway, let's imagine a pipe that's open at both ends. And so, and we'll make it the same length. So we have that going on. All right, well, if it's open at both ends, you have to have displacement antinodes at each end, and you'll have to have in between them, you'll have to have a displacement node. So here's what that sort of wave pattern can look like. And again, keep in mind, the particles are actually going back and forth like this, but here's a displacement node. And so this is a place where they're not doing that. However, this is a fourth of a wavelength. This is a fourth of a wavelength. Here, so anyway, that's the fundamental frequency. Well, how does that compare with this one? It's actually, if you multiplied the top and the bottom of this by 2, you'd have 2V over 4L. It'll be twice the frequency of this one. This will have a sound that's an octave higher than that one because it's got twice the frequency for its fundamental. And I can demonstrate that tomorrow pretty easily with a pipe. And
Professor,
kind of yes.
your screen recording ended.
Oh, shoot. Why did that happen? Well, that's maddening. Let's see. I want to share the screen again, go back to this thing. Share. I don't know if I'm still recording or not. I hope I am.
Your
Okay, well, let's see. Oh, okay. Yeah, if I go up to the recording, I'll pause recording. Well, that's just weird. I don't know why Zoom does this kind of spontaneously, but it does because I didn't touch anything. Okay, anyway, the fundamental frequency for that pipe that's open at both ends ends up being twice as much as that. So I'm going to just make a note of that. It'll be 2 times V over 4L. So twice that frequency. And this is pretty easy to demonstrate. I can do an experiment where I slap a pipe, and if I keep my hand on there, the pipe will resonate as if it's closed at one end. But if I bounce my hand off immediately, it'll resonate like it's this effect. And you can do that at home too if you want. It also works with a vacuum cleaner hose. So you can experiment with that. Well, let's go to the next one up. And this will be same length of pipe again. So L from one end to another. And instead of having one node in there, we're going to have two nodes. So we'll put a node here and a node here. And it's just because I've done this a bunch of times that I know how to make this work. So you can see I'll have an antinode at this end. I'll have an antinode at this end. And halfway between them, I'll have another antinode. So this is more or less what it looks like. But what I've got here now, I've got fourth of a wavelength here, half a wavelength here, and another fourth of a wavelength. That adds up to one wavelength. So here, the length is equal to lambda, and the frequency that I'll get for this mode of oscillation will just be V over L, which is twice the frequency of that one. Here it's V over 2L. This is, whoops, that's supposed to be an L down here. This is 2V over 2L. Okay, because that's the same as V over L, but that's twice the frequency of this one. So that'd be an octave jump. If you double the frequency, the sound will jump by an octave. Let's keep going. And pretty soon we'll be able to write down just a general formula for this. Well, what happens is we'll add another node in here somehow. So I'll have one up here, I'll have one up here, and somewhere, somehow, halfway between them, I'll get another node. So here we'll have something like this going on. Antinode here, antinode there, another antinode here. Whoops, missed. That's supposed to go all the way out there. And then we do this. Okay, full wavelength here, quarter wavelength here, quarter wavelength there. Well, 1 plus a quarter is 1.5 or 3 halves. So here the length is going to be 3 halves of a wavelength. And the frequency, well, solving for lambda, multiply both sides by 2/3. Lambda is going to be 2/3 L, so I'll have V over 2/3 L, which is flip that fraction and multiply, and I'll have 3 times V over 2L. So here it was V over 2L. Here it's 2V over 2L, and the next one up is 3V over 2L. So for a pipe that's open at both ends, the frequencies you get are going to be NV over 2L, but, well, N again is 1, 2, 3, ... But did I copy that down right? Stock pipe. Yeah, that's right. Anyway, here I'll get all the multiples that show up here because I've got that 4 on the bottom. I'll get 1/4, 2/4, 3/4, or actually I end up, oh, that shows up down on the bottom. Open pipe, stopped at one end. Yeah, that should be right. Except I'm wondering if I copied something down wrong. Hang on a sec. I'm a little concerned that I may not gotten one of these quite right, but we'll see. Oh, yeah, yeah, on the one up here, I should have had just odd numbers, 1, 3, 5, and so forth. So this one has all the numbers on it. but this one only has the odd multiples of the fundamental frequency. Okay, that was something that bothered me. So fix that if you wrote it down that way. They also developed this in the textbook, so go ahead and read that carefully and make sure that you get the hang of that stuff. These are fun to demonstrate though, and one of the first things we'll do tomorrow is to actually determine the speed of sound by, we'll have a tube that's like this, closed at one end, and I'll vary the length of the tube by, it's going to have water sitting in the tube, bottom of the tube, and I can change the water level, and we can measure the speed of sound in there by looking for resonances. So kind of fun. Very easy thing. Okay. Fundamental frequency of a pipe that is open at both ends is 594 hertz. How long is the pipe? So what have we got going? Well, it's a pipe that's open at both ends. For that situation, the fundamental frequency has an antinode here, an antinode here, and halfway between it's got a node. So that's the one that looks like this. And rather than just trying to memorize a formula, I draw the picture every time, pretty much. So this is a quarter wavelength from a node to an antinode, quarter wavelength here. So we'll have that the length of the pipe is half of the wavelength, or the wavelength is twice the length of the pipe. The fundamental frequency is going to be V over that simple wavelength that we have there, V over 2L, and they tell me what the fundamental frequency is. The only thing I don't know is how long the pipe is. So if I solve for the length, that's just going to be V over 2 times that fundamental frequency. Well, we're always assuming for sound that we'll have a speed of 344 meters per second. And then I'm dividing by 2 times that fundamental frequency, 594. That's a 2. And I'm just going to call that hertz a per second. And you can see per seconds on top. We'll divide with those per seconds, and I'll have meters here. And there it is. Thought I lost my calculator. Oops, I forgot to wrap the bottom in parentheses, and I got 102,000, which doesn't make sense. So wrap your denominators in parentheses. Okay, there we go. I get 0. Let's see, to 3 sig figs, I would have 290 meters. So 29.0 centimeters, in other words, which is, I don't know how long that is. This thing got that many? Nope. Oh, wait, it does. Yeah, on the other side. That would be about how long the pipe happens to be. So you can see that whole thing. Okay, if one end is closed, find B, the wavelength, and C, the frequency of the new fundamental. Okay, well, we've got enough information to do that. We know what L is. And so there's going to be a new fundamental that'll be, remember, at the closed end, you have a displacement node. So here's what we'd have. And this is 1/4 of a wavelength. from the closed end to the open end, and that's L. So here, that means the wavelength is going to be 4L. So lambda equals 4L, which is going to be 4 times 0.290 meters, which is I get 1.16 meters for that wavelength. And the frequency is going to be V over lambda, which is 344 meters per second divided by 1.16 meters. And we should get something that's less than that anyway. And I get about 297 per seconds or hertz. Okay. Well, if I double that, I get back to 594, wherever it was there. So then you could hear that difference pretty easily. So a couple of really basic problems there for our introductory stuff. Okay, now a human body thing. Now, the human vocal tract is a pipe that extends about 17 centimeters from the lips to the vocal folds, also called vocal cords, near the middle of your throat. The vocal folds behave rather like the reed of a clarinet, and the vocal tract acts like a stopped pipe. So we can just treat this thing as a stopped pipe here. Whoops. Yeah, that more or less does the thing. 17 centimeters. Estimate the first 3 standing wave frequencies of the vocal tract and use V equals 344 meters per second. And the answers are only an estimate because you can vary it with the lips and the tongue. And you can also vary it by changing the pressure within the vocal tract. And you do that by contracting the diaphragm while you're singing. So although most people don't think about contracting the diaphragm while they're singing, but that's the effect that you have. And because you contract the diaphragm, you increase the pressure, and that makes the speed of sound greater. And because the frequency is equal to the speed of sound divided by the wavelengths, you can change the frequency by increasing the speed of sound, which you can do by increasing the pressure in your vocal tract. So big fun, all kinds of stuff going in here. So here we've got 1/4 of a wavelength in here, it being the stopped pipe. Those are the ones where we'll do the odd multiples of the thing, but I'm going to draw the pictures anyway. So the frequency in this case will be V over the length is actually 4 times, or the frequency is actually 4 times the length. So 4L, excuse me, and we can just figure out that frequency. We'll assume 344 meters per second for the fundamental, although you can vary that when you're singing. So although you aren't usually thinking of varying the speed of sound, but people would think you were a nerd if you talk like that. 4 times the 17, or 0.17 meters. Can you switch instantly from numbers of centimeters to numbers of meters? That's a nice thing to be able to do at any rate. That should be 0.68, 4 times that. And I get 500, and we can only keep 2 sig figs, so I'll call it 510 hertz. So, which isn't all that low a voice or low a frequency. Okay, well, what's next? We'll do this would be the second standing wave frequency. This is one where we have a node here, and an antinode up there. So this time we have a half plus a quarter. So the frequency is going to equal V divided by the length is equal to 3/4 of a wave. The wavelength is going to be 4/3 of the length. Maybe I should write that out. L equals 3/4 of a wave. So lambda is 4/3 of L. So this will be 3 times V over 4L. Well, we had V over 4L there. We just have to triple that. That's going to be 1,530 hertz. Well, that 3 is an exact thing. All right. What next? Okay. Estimate the first 3 standing wave frequencies. Okay. Well, the next one, I'll have 2 of these nodes in there in addition to the one down here. So something that looks like this. And it should be 5 times that frequency because they're odd multiples on those things. Okay, full wave here, 1/4 of a wavelength here. That means L, 1 plus 1/4 is 5/4. L is 5/4 lambda, or lambda is going to be 4/5 of L. The frequency here is going to be V over lambda, which is V over 4/5 L. And that looks like 5 times V divided by 4L, which is 5 times that frequency. So I just multiply that by 5, and I get 2550, I think. Hertz. Okay, there's a lot more complications to singing than just getting things like that. But those could be things that if a person were singing this note, these would be overtones that would be part of the total sound. And so if you did a spectrum analysis of the sound, you can actually split out those frequencies and see what they are and how their amplitudes, what their amplitudes happen to look like. Okay. One more here. A certain pipe produces a fundamental frequency of 262 hertz in air. So I think we figure out some stuff related to that. We could figure out the length of the pipe for one thing, but maybe we don't have to. Let's see, what do they tell us about this? Actually, we don't know. If you fill it with helium, seems like the only way we could fill it is if it's in an environment that's all helium. So maybe you've got some kind of a chamber where you can have the pipe sitting in there. You can make it resonate, and then in the chamber that it's in, you pump out all the air and let in helium. I guess we would do that. So Let's just imagine that this is something, some kind of a pipe or other. And if it's a pipe that's open at both ends, wherever I put those things down. This is supposed to be 1, 3, 5. Its fundamental frequency will either be V over 2L or V over 4L, depending on whether it's open at each end or, excuse me, or open at one end and closed at the other. But we would get something like that. However, you can see it depends on the speed. So either V over 2L is equal to 262 hertz, or V over 4L is going to equal 262 hertz. But let's go ahead and use this scary looking formula, which we've got all the numbers for, to calculate the speed of sound in this new medium. So we'll do it for air first. Let's see. We don't even know what the temperature is. So we're kind of stumped here, but I'll have V air is going to equal the square root of, this is the Greek letter gamma, by the way. Gamma for air times R times some temperature. And we don't know the temperature, but we do know we've got the molar mass for air, which is 28.8 gram per mole. And what I'm going to do is, and I could plug in R. I don't see that it mentions a temperature here at all. So I'm just going to pretend I don't know it. But for helium, you could calculate this. You'd have V sub HE, and it's going to be the square root of gamma for helium R, same temperature. I'm assuming we're not changing that. And I would divide that by 4.00 grams per mole. And I think if I take the ratio of these two things, for one thing, R will divide out, T will divide out. I'll end up with just these things left and just those things left. And I can figure out how many times greater the speed of sound in the helium is. And then I can just take that fundamental frequency and multiply it by that to figure out what that'll be. So let's do that. V sub HE over V sub air will equal. Oh, don't worry about the fact that you have no idea where that formula came from. It comes from some stuff involving thermodynamics and fluid mechanics, and is beyond the scope of this course. So that's kind of dodging the question, but that's okay. I'd have gamma HE, RT, I'll have, actually, I'm going to write it as M sub HE because I just don't want to have to keep writing 4.00 grams per mole. And at the end, I'll plug in the numbers. So we'll see what that works. And then on the bottom, we'll have gamma sub air. We'll have RT, and we'll have the molar mass of air. Well, you've got a square root on top and a square root on the bottom. It can be the square root of the whole thing. And under that whole thing square root, you'll have a fraction over another fraction. You can take the bottom one and invert it and multiply. And we will have, let's see. I'll write the top one first, gamma HE RT over molar mass of the helium times the inverse of this one, the molar mass of air. divided by gamma for air times RT. Cross out the things we don't know or that divide out. And what I end up with is VHE over V air is going to equal the square root of gamma for helium, which is 1.67, times the mass, molar mass of the air, which is 28.8 grams per mole. By the way, that gamma is something, it's different for helium than it is for air because helium is monatomic. It's single atoms. And for air, it's pretty much all diatomic, except for some argon, but it's mostly nitrogen and oxygen, both of which form diatomic molecules. And that's something that comes out in thermodynamics. If you get far enough, you'll learn about diatomic versus monatomic gases. And we will have a unit on thermal at the end of the quarter. Let's see, gamma for air was 1.40. And then we've got the 4.00 grams per mole for that. And if we do that, whoops, turn on calculator first. Yes. Okay, and I get about 2.9. I guess we have 3 figs, so 2.93, which means the speed of sound in helium is almost 3 times as much as the speed of sound in air. And so those fundamental frequencies, it doesn't matter which one it happens to be, since it's proportional to the speed of sound. The speed of sound is going to be 2.93 times as fast, and so it'll be 2.93 times what that is. So the fundamental frequency for HE, I just take the number and multiply it by 262, and I would get about 768. Since it's something that's almost 3 times as much, that would be an octave and a fifth above the frequency of that other one. So quite a bit higher. And that's why people sound like chipmunks when they inhale helium and talk. Which I say probably isn't a great idea for reasons I'll explain. Nearly all of the helium that you get here is something that's a byproduct of mining for natural gas or extracting natural gas from underground. And natural gas collects in these pockets underground, and it's kind of impermeable above those pockets. If it was underground that wasn't impermeable, the natural gas could leak out, so could the helium. But anyway, it's in these pockets underground with natural gas, which is a petroleum product. And they usually either just exhaust the helium to the atmosphere. It's a harmless gas, but sometimes they collect it. It's also a product that you can make money on, but it's not, you're not going to get rich. But anyway, they collect that helium, and if it's not purified, it can have petroleum distillates, things that is part of the natural gas and petroleum stuff that's underground where it is. And those things you want to inhale into your lungs. So if it's not pure, you can get those in your lungs, and that's harmful. Helium itself is not harmful. It doesn't form any chemical bonds. It just is harmless. I don't know if I mentioned this, but nearly all of the helium that comes up in that natural gas mining comes from the decay of radioactive isotopes farther down in the earth. They decay by alpha decay, which is where a particle with 2 protons and 2 neutrons comes flying out of the nucleus and picks up a couple of electrons, and instead of being a helium nucleus by itself, it becomes a helium atom. And so that's where that stuff comes by. Once that process is done, the helium that's produced is completely harmless. Okay, it's not radioactive. Helium-4 is one of the most stable isotopes there is. In fact, it's also one of the nuclei that's hardest to split apart. They don't come apart or do anything. So you've got this harmless stuff that's the result of radioactive decay, except if that harmless stuff is mixed with petroleum byproducts, then it's not so healthy. But I have to confess, I have inhaled helium from the balloons you get for parties and stuff like that, even though it could be risky. But because it's not a product that's made to be used by humans or inhaled by humans, and they don't have to have any sort of standards on that helium at all. So be careful if you do that. But it does sound neat. And when they people who scuba dive at great depths, the at the pressures that they have there, nitrogen will be kind of the nitrogen that you breathe can be absorbed into the bloodstream and happens. And if you come up too fast, that nitrogen that is in your bloodstream that usually isn't there, or it's usually a gas when you're but anyway, that nitrogen can form bubbles in your blood, and it can end up blocking the flow of blood in your joints and things like that. And that's what's called the bends, the BENDS. And people who scuba dive have to come up very slowly, and they've calculated just how long they have to be at different depths. But by coming up very slowly, that nitrogen that's in your blood can gradually work its way out of there as you're coming up to these different levels and different pressures underwater. And so it can come out of your blood slowly. Or instead of having nitrogen mixed with the oxygen, they can have helium mixed with the oxygen. And if that's the case, then you don't have to worry about the bends. You just sound like a chipmunk when you talk instead. So, okay, that's kind of far afield. Tomorrow, I'm not going to talk much about resonance at all today, but tomorrow we'll look at some resonance for some different pipes and things like that. And it's interesting what an effect getting just the right frequency on a tube of air will have. One thing I'll do is I'll take a tuning fork and hold it above a tube that has water in it part way up, and I'll just hold the tuning fork vibrating up there above it and let water drop out of there. And at certain points, all of a sudden the tube will start resonating loudly and you'll be able to hear it. And it's kind of neat seeing how something that isn't really very loud, when you get it near a system that can vibrate at the same frequency as it, will produce quite a loud sound. So we'll do a little bit with that. But stop for today. I don't know if any of you got the email. I think I had a few people, about 4 people, respond to it already, that I am willing to hold a meeting this evening or late afternoon to answer questions you might have about homework 2. And so check your Canvas messages for that and respond to that thing if you're interested in going to that or attending. And I'll pick it at a time that most people can do. It's not gonna take all that long. It'll be a fairly short meeting, but you know, maybe half an hour and you'd have whatever questions you have answered. But if I hold the meeting for an hour, you might be able to show up after half an hour and still have your questions answered. So I'm willing to do that, but I'll pick some 1 hour set where that's the most convenient for people. And so I'll see you then.